Okay, so let's just check things out here. And we're going to learn some pretty cool stuff today. The big thing that we're going to learn today is the momentum impulse theorem. It's an extension of this theorem. Now, what you learned previously is that the impulse acting on an object is the average net force multiplied by the time that that force acts for, and that's equal to the change in momentum. And the units for this are Newton seconds, which is the exact same thing as a kilogram meter per second. Now, you've already downloaded this worksheet or this lesson sheet, so you're just following along. Maybe you can add that a little bit up here. So this is the big thing. This is Newton's second law written as it originally would have been written. So here's what Newton actually wrote. His notation was a little bit different, but he did this nonetheless. So what he looked at was, he said, the time variant net force right here. So sigma F is the net force as a function of time. And it's time variant, meaning that the force can change over time. So the force doesn't have to be constant. It could go up and down, be negative, positive, whatever the case may be. It's a function, basically. And how he originally wrote Newton's second law and how Newton wrote it was the change in momentum over the change in time. Now, the equation that we've been using is delta P divided by delta T. Will tell you what the average net force is acting on an object. Well, these deltas are secant lines. So it's looking at the average momentum change over the average time. So what is the change in momentum from one point to another point divided by the time? That is a secant, and that is the average net force acting on the object. You did this in calculus. Now, if you didn't do calculus, just follow along. Doesn't matter. In this course, I'm going to show you how to solve these problems using an online applet and also just by guessing. You don't have to be able to do the calculus for this, but if you've taken calculus or are taking calculus, this is going to be very helpful for you because it's the next level of learning for university. So don't stress either way. I'll do some practice with it, but you're not being evaluated on it. Now, this is the dp by dt is the change in momentum over the change in time, but it's instantaneous. So this is the tangent line. So this, by doing the derivative, is the tangent line to the curve, whereas the other one is the secant line, the average between 2 points on the curve. This is at one particular instant in time. So it's the time variant net force. It's not the average at this point. Now, what we can do is we can rewrite momentum as m times v, right? Now these are vectors, so I'm going to write the vector sign here and here, but we're going to realize that just, oh boy, don't put it on top of that m. And what you'll notice is that we're just going to drop it because we just don't want to write it over and over. So momentum is mass times velocity. Now, if the mass is constant, the derivative of a constant is 0. So it doesn't count. So if we use the chain rule, the derivative of mass times the v is 0 plus the derivative of v times m, which is what the term you have here. So the other term that was missing was the plus the derivative of the mass times time, which is, in some instances, does change. If you're talking about a rocket ship, as you're expelling fuel out the bottom, the mass is changing. So if you want to solve a rocket problem, literally rocket science, you would include the plus dm by dt times the speed at that point in time. It's not hard to do. You can solve it, and you can actually do real rocket science calculations. Now, assuming that the mass is constant, we only end up with this part of the term. Now look at this. Change in speed over change in time. I've heard that before. v2 minus v1 over delta t. Oh, that's just the acceleration of the object. So, if this was Newton's second law, it was m times the change in speed over the change in time, which is acceleration. And that's how we always think of Newton's second law. But really, it was the change in momentum over change in time. So now let's write out the momentum impulse theorem. So that should be pretty cool if you see that now and you can think about that. Now, the impulse theorem. All right, you ready for this? So for the momentum impulse theorem, what we're going to have is we're going to multiply the t, the delta t, or the dt, sorry, up to the other side, and we get this situation here. We have sigma f of t, which is just the time variant force, times the dt equals mdv. Now here we have something called j. J is the equivalent, in this case I is equal to j. It's just the impulse. A lot of textbooks use j instead of I. So I put it as j, you can just write it as I. It's up to you. Here's the cool part. We're going to introduce these things here, these integral signs. Okay? So in math, the secant, the delta, becomes the derivative. So this is the average. This is the instantaneous, or the what we call the continuous. This is sometimes called the discrete, and this is sometimes called the continuous. So we should actually use that. So this is called the discrete, and this is the continuous. Okay, so deltas become d's, sigmas become integrals. This means a change, this means a change. This means add up, this means add up. I'm going to say it again. Delta means change, or the average change, instantaneous change. Sigma is the average addition, so when you're talking about adding up forces, you add one force plus another force plus another force, subtract another force, add another force. It's addition. This is the summation, which is actually what that means. An integral is also a summation for a continuous curve. I'm going to say it again. Delta is the change. D is also the change. Average change, instantaneous change, discrete, continuous. Sigma is the addition or summation, hence why it's an S for sigma. The integral is the continuous version of an addition, of summation, of adding. And you're thinking, what are we adding? Well, here we go. So what we do is we say, let's integrate this. And we're going to integrate it from t1 to t2, so time 1 to time 2, and then from a speed of v1 to v2. Now, what we're going to see here is that if mass is constant, you don't have to know any of this. This is for next year anyways, but it's just interesting to know. If mass is constant, it can come outside of the summation or outside the integral, and you're left with dv. Well, if you integrate dv from v1 to v2, an integral and a derivative undoes each other. So an integral of a derivative undoes the derivative, or the antiderivative. Now, since this is just dv by itself, the integral sign in the d becomes v2 minus v1. This is the fundamental theorem of calculus, actually. Something you will learn in university. What is v2 minus v1? Delta v. Well, what does m delta v represent? The momentum, or the change in momentum. Okay? So you're like, oh, impulse equals change in momentum. So this last term here says if we integrate the force over some time interval from t1 to t2, if we integrate it from t1 to t2, it tells us the impulse, or it tells us the momentum change. So I'm going to say this again. Here, this integral undid the derivative, and since it's just dv, it becomes v2 minus v1, final minus initial. That term there, m delta v, is by definition the change in momentum. Change in momentum and impulse are the same thing. So it's this term here that we're focusing on. So if we integrate the force over some time interval from t1 to t2, it will tell us how much impulse there was or how much the momentum changed. Well, think about this. What did we just learn the other day? We learned that if we have a force-time graph, force, time, and we have a graph of it, a function, and what did the change in momentum or the impulse represent on that graph? It represented the area. Okay? If I had a strange looking function for the net force over some time interval, like this, if I said integrate from t1 to t2, I said do this term here, let's do the integral of t1 to t2, it will tell us the change in momentum. But that's just the area. So by doing the calculus of this, it will tell you what the area is, which is your momentum. Now, it's easy for lots of functions if they're just straight lines. But if it's an actual function, you need to actually do some math. All right, so in general, what we call this is in general, we say that if we integrate from a to b, or take the antiderivative, it says undo the derivative and evaluate at a and b. And then you subtract them. So this gives you the area bounded by the function and the axis that I drew in this picture here. Okay, so you're like, great, thanks a lot for that. Now, doing the antiderivative, we're only going to do simple functions, and then we're going to use Wolfram alpha to do the harder ones for us. Whenever you're integrating from a to b, what you're doing is you're taking the value at b and subtracting the value at a, just like we did up here. So the next thing we're going to do is I'm going to show you some examples of how to do this. I'm going to show you how to do it using calculus. I'm going to show you how to do it using Wolfram alpha, and I'm going to show you how to guess at it, a three-step way of doing it. You can always use Wolfram alpha, and you can always do the guess. And if you're comfortable, try the antiderivatives or the calculus version. Okay, so that'll be in the next tutorial, and hope that wasn't too bad for you.